Good evening, everyone. We are in the week 8 problem solving session of the NPTEL course Network Analysis, and week 8 is about graph theory applied to network analysis. I am Teja Golla, a fourth year research scholar working under Dr. Santanu Kapur at Embedded Power Management Lab, PE Department, IIT Kharagpur. Let me share my screen. So before we start, I would like to ask you one thing. So should I cover the concept because like this week session is a little bit simpler if you understand the concept. So if you understand the concept, problem solving will not take much time. So if you are okay with the concept, then I will spend very less time on the concept and we'll spend more time on the problem solving session. But if you want me to teach like the concept, then we might have to spend around half an hour to 40 minutes on the concept overall and then solve the problem solving session. So which one would you like me to consider? Only problems or concept plus problems?
You just touch up the concept and
Okay. Then we'll spend some time, relevant time on the concept, and then we'll go to the problems. Okay. So first thing is, why do we need graph theory? So
Sir, good evening, sir.
sorry.
Good evening, sir. Sir,
Good
the
evening.
last week assignment, first problem I couldn't solve. If time permits, please explain, sir.
Okay. I will keep this in mind. So this week problem solving session will not take much time. So once we are done with the problem solving session, you please remind me. Towards the end, we can solve that problem.
Okay, sir.
Okay. So we'll quickly go through the concept. It is simple only, but the terminology is important. Like what is graph, what is node, what is tree, what is twig, what is link, what is code tree. All these we'll cover so that you'll be thorough with the nomenclature. So why do we need graph theory? So when the complexity of the circuits increases, then you cannot solve them by hand, right? Say if the number of we are basically dealing with second order system, so it has certain equations. Say I have or two loops or three loops where we can solve by hand, like three loops. Say the number of unknowns are more than three. Say we have 10 number of unknowns, then we cannot solve it by hand, right? We need a computer so that it can solve that. But how do we make the computer solve, right? We need to give the computer some expression so that it can solve mathematically. But who will give that expressions to the computer? Say we have a large network which has say 10 sources and 20 components or elements, circuit elements. Then first someone has to write down the equations and then feed it to the computer. So computer will solve. But the process from understanding the circuit to writing the equations, that is also a difficult process. So how to write it in a systematic way so that it will be easy for us also. And then once we get in a proper format, we can feed to the computer and computer can solve. So for that purpose, we need graph theory. So it's like a systematic guidelines or a procedure to solve the circuit by putting it in a nice way so that it can be solved using any mathematical toolbox or a computer. So that's why we need graph theory. So we'll solve the any circuit in a proper way. So we basically convert it into matrices. So now these matrices can be fed to any computer and it can solve matrix because it will perform the inverse matrix. As a human, we cannot do if the order of the matrix goes above three. So when the complexity as well as the order of the system increases, we have to use computer, help of computer, but we need to plug in a particular way, which can be done using graph theory. So that is the overall basic idea. So as the complexity of the circuit increases, we need a systematic way systematic by writing backward this. So, So we need a systematic way to solve the circuit, and we use graph theory to do so.
Sir, letters are not shown, sir.
Sorry,
Sir, the letters are not shown. Only it stopped up to systematic. We need a systematic.
you are not able to see
Ah, yes, sir.
everyone.
Yes, sir.
Okay, let me reshare and just check. Now are you able to see? Can you see my screen?
Yes,
Ah, yes,
sir.
sir.
You can see we use graph theory, right?
Yes, sir.
Okay. Okay. So we use graph theory to do so. But like, should do you know what is a graph, or should I explain that also? So if you don't know, then I'll explain. Else I can skip. Like, what is graph? How to draw the graph of a circuit? Is that clear to everyone, or should I cover that aspect as well?
You covered that, sir.
Okay, then I'll cover. So any circuit that can be given, it has to be first converted into a graph. Graph is like a skeleton of the circuit. So how are we going to draw that graph, and what is a graph? What information does a graph consist of? So that we'll check. So we'll discuss about few things. One is graph, and another one is directed graph. So let me consider one circuit that sir has considered in his while teaching in his notes. So let me quickly draw that circuit. So these rectangular boxes are elements. It can be a combination of voltage, current source, resistor, inductance, and capacitor. But it is just it can be anything, any combination of that. But we are representing that entire branch as a some box, which we are calling it as an element. So now the current is flowing. So take the note of the direction of the current. Say the current is flowing like this. Say IE 6. Then it is plus, it is minus, because the current is flowing from a higher potential to lower potential. So first, let us mark the nodes. There are how many nodes? Four nodes: A, B, C, and this we can call it as O, which is our reference. And the elements. So elements have element voltage, element current. So we'll consider the same way how sir has considered. So once we know the direction of the current, then we can know the polarity, because the current is flowing from high potential to lower potential. V1, then IE2 plus minus VE2, then IE3 plus minus VE3, then IE5 plus minus VE5. So this is the circuit. So this is like a given network. So is the convention clear to everyone? Like the convention relation between the direction of the current as well as the voltage polarity?
Yes, sir.
Okay. So now graph means how we are going to draw the graph. So graph means basically first we'll draw the nodes. So we have A node, we have B node, we have C node, and then we have O node, right? Say here. Now we'll just first let us write, this is A node, this is B node, this is C node, this is O node. So now each branch will be represented just by line. So A to B, there is one branch. So A to B, I'll draw one line. B to C, then B to O, then O to C, then A to O. Maybe I'll use a different color for note so that it can be seen. So basically the left circuit I am representing in a like a skeleton. So I have removed everything, and I have just mentioned what are the nodes and what are the connection between the nodes. Like the elements I am representing by a straight line. So this is basically called as the graph of the network. So is this clear? Like how we are drawing the graph of network? Simple. We'll just represent the branch by a line.
Yes, sir.
So now this graph does not have any information regarding the voltage, regarding the current, regarding anything. It is just a line. So it is just basic graph. So what is a directed graph? Directed graph will have some information regarding the direction of current as well as voltage polarity. So let us consider the same figure and then we'll write the direction of the current, voltage, everything. So from the top, directed graph. Now we are drawing this. Sorry, from the top graph, we are now drawing the directed graph. So what I'll be doing is I'll put the current as well as the voltage information. So I'm using a different color. So it has IE4. So basically what I'm doing is whatever is the direction that is mentioned here, I'm just putting the same. So A to B, if you see, current IE4 is flowing and VE4. Similarly, A to O, IE1 is flowing and voltage is VE1. So this is IE1 and plus minus VE1. Similarly, here IE2 is flowing from bottom to top, and this is plus minus VE2. And then here direction is IE2, and the voltage is plus minus VE, sorry, IE3. This is VE3. And similarly, the current is IE5. So this is plus minus VE5. Basically, I am adding all the current information as well as voltage information. So this is called directed graph of the network. Directed graph of the network. So graph means it doesn't have any information, whereas directed graph on the other side, it has all the information. Now looking at this, I know that there is a element, circuit element from A to B, which is carrying a current of IE4 with a voltage VE4. So looking at this, I can redraw this circuit, right? So I will be able to redraw this circuit from this. However, I cannot do the same from this circuit. So this is just basic skeleton. This has the information. So is this clear? Directed graph.
Yes, sir.
But if you see, if I know the direction of the current, then I know the polarity of the voltage, right? So both need not be drawn, right? Because if I know the direction of the current, then I also know the direction of the, sorry, polarity of the voltage. So this is IE6, I3. So I need not mention the voltage polarity as well as current direction both, because one is dependent on another. If I am aware of one thing, the other one will be automatically known. Agree? Or any doubts? Is it clear? Like what I'm trying to say is, if I know the direction of the current, then I also know the polarity of the voltage, right? So if I give the direction of the current, I need not write the voltage information. Because if this is IE2, I know that the bottom terminal is positive and the top terminal is negative, and it is VE2 because it is branch 2.
Sir, but polarity changes with respect to source and resistant elements.
Like this is a generalized polarity. Like here VE6 can be positive or can be negative, but we are generalizing something, right? So when we are developing a theory, we are fixing one polarity and using that polarity, we'll solve the circuit. Now after solving the circuit, we can get IE6 equal to 1 ampere or maybe minus 3 ampere or 0 ampere. Whatever the value that we'll be getting, that's a different story. But when we are starting, we are assuming some polarity and we are following the same polarity. Uh, does that make sense?
Clear, sir.
Yeah. So now the convention that we have considered is what we all know, like the current is flowing from positive terminal to negative terminal. So if this is the direction of the current, this is positive, this is negative. So now if you look at this circuit also, it is looking so clumsy, right? Because there is so much variable, so many equations. Looking at this, like it is very clumsy. So now what we'll be doing is, instead of writing all those details, we'll write just the number of the So we'll write which element is what. Basically, what I'm trying to say is, say this is element 6, so we'll write element 6. This is element 4, so we'll write element 4. This is element 3, so I'll write element 3. This is element 2, so I'll write 2. This is element 1, so I'll write 1. This is element 5, this is 5. So now if I give you this circuit, from this circuit, or say graph, I should be more precise. So from this graph, you can draw this graph, right? Because if this is the direction of the current, and if this is element 6, then the voltage is plus on the minus, minus on the right, and V is 6, and the current is I is 6, because it's all generalized statements. So from this graph, I can draw this graph. And from this graph, I can draw the original network. So I can represent the original network in this graph, so that it will not look clumsy. Also, it will have some information, unlike this graph, which doesn't have any information. So this is called a simplified directed graph, because it's a simplified version of the directed graph. Is it clear?
Yes, sir.
So this is what we will be using today, or throughout this course whenever graph comes. So this is used in this course. This graph will be used for analysis, because it is simple. Also, it has all the necessary information. So that's why we are going to use this graph. Now, before we go into any sort of nodal analysis, mesh analysis, there are some, like nomenclature that is very important. And that also was covered by sir. And I'll be covering this nomenclature because it is very important to understand. And we'll be using this type of, this graph only, this example, for understanding the nomenclature. And this nomenclature is very important. So if you have any doubt, please stop me and ask. Because over the time when we solve the problems, I will use that nomenclature rather than again explaining it. So first we'll be learning about tree and poetry of a graph. Tree and poetry of a graph. So before we go any further, first let us define the number of elements. So how many elements are there? So elements are like the branches. How many elements are there in this circuit? Sorry,
6 elements are these.
6 elements. And how many nodes?
4 nodes.
4 nodes. Yeah, very good. Okay. So then we'll come back to something called number of twigs and number of links. So I'll leave 2 lines, and then first we'll get back to what is a tree. So now we are asking what is tree. So tree is something you get by joining all the nodes so that no loop is formed. Say A, B, C, and O. I have to join A, B, C, and O using these elements like 1, 4, 2, 3. So there are multiple possibilities. So now I have to join this so that no loop should be formed. So like how you will get tree? A tree is formed when you connect all the nodes. A tree is formed when all the nodes of a given network are connected without forming any loop. Without forming any loop. Say, let me consider one example so that it will be easy. So in this case, say I will use 1, 2, and then 3. So elements I will be using element 1, element 2, element 3. So let me draw. Okay. Or maybe I'll draw this again at the bottom so that you can correlate rather than scrolling up and down. So this is the element, this is the thing we have. So now what I'm trying to say is we have A, B, C, O. So I use this one, I use this one, and I use this one. So these are our nodes. So now if you see, I have joined all the nodes and no loop is formed. So this is element one, this is element two, this is element three. I can do it in multiple ways, right? I can use 2, 4, 6, or I can use 1, 5, and 3. So there are multiple possibilities, but here I am considering one of the possibility. And now once I do this, this is called tree. So this is called tree. So this is called tree. Clear or any queries? If you have any doubts, please ask because it is very important to understand tree, code tree, everything. If you have any small doubt, please ask because this is very crucial and fundamental. This is just one possibility of tree. There are n number of possibilities depending upon how many elements are there, how the circuit is there. Any
Clear.
doubts? Clear. Okay.
Understood.
So now what are the elements of the tree? Elements of the tree are called twigs. So twigs. Elements of the tree. Elements of the tree are called twigs. And how many twigs will be there? Always n minus 1. Say if n is the number of nodes, then we'll have always n minus 1 twigs because say 1, 2, 3, 4. 4 nodes are there, right? So I'll go from 1 to 2 node, 2 to 3 node, 3 to 4 node, but not 4 to 1 because if I do that, then loop will be formed. But loop should not be formed because that's how tree is defined. So always we'll have the number of twigs, which is n minus 1 because we are not, we are just going from node 1 to node n. You can say like node 1 to node 2, node 2 to node 3, node 3 to node 4, up to so on, node n minus 1 to node n. So you'll have n minus 1 branches. So it is twigs because it's the element of tree. So number of twigs which are defined by t is equal to n minus 1. So here we will get 3. So t is represented per number of twigs. So is this clear how we are getting n minus 1?
Yes, sir.
Now tree is given. What is cotree? So cotree is simple. The elements that are absent in the tree, they are called, they will form a cotree. The elements that are absent in the tree form a cotree. Okay. So what I mean by that? So let us consider the same example. Then okay. So now this is tree, right? So what are the elements that are absent in the tree? They will form the cotree. So let me use a different color, blue color. Say this element dotted line is absent. So this forms cotree. Okay. So the solid black line corresponds to tree, and then the dotted line corresponds to cotree. So basically, if I have to draw cotree only, then I will draw something like this here, and basically this is cotree. Whichever are absent in the tree, given tree. So for a given tree, there is one cotree, but trees can be like different, right? I can also consider 4, 2, and 5. So for this tree, there will be a different cotree. So we are talking about one particular tree. For this tree, this is the cotree. Like whichever elements are absent in the tree, they form a cotree. But because a number of trees exist, similarly, number of many coteries also exist. So this is cotree. I have just drawn both on the same figure. Is this clear or Any doubts until this point? I hope you are following. Everyone following?
Yes, sir. Yes, sir. Understood.
Yes, sir.
Okay. So now elements of tree are called twigs. What are elements of core tree called? They are called links. Links. Elements of core tree are called links. Okay. So how many number of links we'll get? So number of links, which is represented by small l, is number of elements E minus twigs, because tree plus core tree forms the given circuit, right? So uh, like if you see, tree has, what are the number of elements of tree, which are called twigs, and what are the total elements? E. So number of elements in core tree are E minus T. So number of links are E minus T. So it will be E minus n plus 1. So E is 6, n is 4, 2 plus 1, 3. Clear?
Yes, sir.
Okay. So now this completes the nomenclature. Now we'll move to nodal analysis, mesh analysis, and then cut set theory. So we'll cover each topic and then we'll solve one problem on each of them. So first, I hope things are clear. The nomenclature, everything, the notation and the representation, like how we represent them, their what are they called, everything. So now we'll go to one simple graph theory and nodal method. So we'll start with the nodal method. Graph theory and nodal method. So basically, we are applying nodal analysis, nothing more. So we'll consider this example and then we'll apply here. Or even we can, so let us consider this example. Because this is not needed. So for the others, we need to know trees and co-trees, but for this method, we don't need trees and co-trees. Basically, we'll apply KCL. So this here we are applying KCL. KCL needs to be applied at n minus 1 nodes, because like you need not apply KCL here and here and here and here, because if you are applying three, like here all three nodes, then here you need not apply, because the number of unknowns are, like, say this is ground, say if this is ground, this is VA, VB, VC, right? So basically in this circuit there are only three unknowns. So basically you need three equation, and the fourth equation is not needed. So you can apply KCL here, here, here. Any three nodes you can apply KCL, because fourth equation will be dependent on the other three equations, because the circuit has basically three unknowns. Is that clear? Hello.
Yes, sir.
Hello. Any doubts?
Yes, sir. Clear, sir.
Clear. Okay. So the convention that will be considered is current leaving the node is positive. Current leaving the node is positive, and then current entering the node is negative. Okay. Now let us apply KCL at node A. So can anyone tell me what is the equation following this convention? Current leaving is positive and current entering is negative. So KCL at node A, what currents are leaving? IE1, IE4 and IE6, right? So what will be the equation?
So IE4 plus
Okay.
IE1 plus IE6.
Yes. IE4 plus IE1 plus IE6 is equals to 0. Everyone agree or any doubt? Okay. Node B, what is the KCL at node B? Current 4 is entering, 2 is entering, and 3 is leaving.
IE3
Okay.
minus IE4 minus IE2 is equal to 0.
0. Very good. Now KCL at node C.
IE5 minus IE3 minus IE6.
Minus IE3 minus IE6 equal to 0. Very good. So we have three equations. Now we are going to write it in a different format. We are going to write it in a matrix. First, let me just write so that you can understand how we are writing. If you have any query, then you can ask. Uh, so we have basically elements. How many elements are there? 6, right? So I am writing 1, 2, 3, 4, 5, 6. Then we have KCL at node A, KCL at node B, KCL at node C. And the terms I'm writing KCL at 0, because KCL at node A, I have to check whether IE1 term is there or IE2 term is there. Say IE1 term is there, right? So I'll write 1. IE2 is not there. So I'm talking about this equation. Equation 1, equation 2, equation 3. So if element 1 current is there, then we'll put 1. If it is -1, we'll put -1. If it is not there, we'll put 0. So KCL at node A has IE4, right? So IE4, IE1 and IE6. And other terms are 0. Now KCL at node B is IE3 minus IE4 minus IE2. Other terms are 0. KCL at node C, IE5 minus IE3 minus IE6. Other terms are 0. So basically, now let me complete the matrix format I'm writing. This into we have IE1, IE2, IE3, IE4, IE5, IE6. This into this is equals to 0, 0, 0. So I can write the above three equations in this format. Agree or just check and see what I have done. I have written in terms of matrix. I have written some matrix into element currents is equals to 0. So basically 1, 2, 3 equations I have written in a single matrix equation. Is this clear or any confusion or any doubts?
Yes, sir.
Clear, everyone? Shamita, Nandini, Murugan and
Yes, sir.
Parvatam.
Yes, sir.
Clear, right? Yes. So now we represent this as a matrix. So basically, we are representing this as matrix A, and we are representing this as matrix IE. And this is also not just 0, but it is 0 matrix. So now we have one equation which is matrix A into matrix IE is equal to matrix 0. So this is what we got. So now what will be the size of matrix A and what will be the size of matrix IE? So if you see, matrix A is obtained by applying KCL at n minus 1 nodes, right? So the number of rows are n minus 1 and the number of columns are elements. So n minus 1 cross number of elements. Whereas IE is element currents, right? And it's a column vector. So it has E rows and 1 column. Is it clear how we are getting the matrix size. So basically, I'm writing what is the size of this matrix, size of this matrix. Here, number of rows are n minus 1 nodes. So n minus 1. Number of columns are elements. So E. Here, number of rows are number of elements and number of columns are 1. So it is n minus 1 cross E. It is E cross 1. Is this clear or any doubt?
Clear, sir.
Clear. There is another name for this element A, for matrix A. So matrix A is called as reduced incidence matrix. Reduced incidence matrix. And these are nothing but element parameters. Clear, right? Or any doubts? This is just the name. So in the exam, maybe they can ask, find the reduced incidence matrix. So you have to understand that they're asking basically A. So how will we calculate A? We'll calculate by applying KCL at nodes. So they will give at what nodes you have to apply, because you can ask, sir, I can apply at OBC, at ACO, right? Because it has to be applied at 3 nodes. Usually they will give what nodes you have to apply. If one is connected ground, then you have to apply at the rest, because depending upon where you are applying, the matrix will change. So they'll mention at which nodes you are basically applying the KCL, and accordingly you have to get this matrix. So this is very simple. Just to summarize, we are applying KCL at n minus 1 nodes because it has n minus 1 unknowns. Current leaving the node is positive, current entering the node is negative. With this convention, we are writing the equations of KCL at each node, and then we are representing these 3 equations or n minus 1 equations in terms of a matrix. Now we are getting A, which is reduced incidence matrix, and these are element currents, and this is a zero matrix. So I can also write what is the size of 0, because it's not just 0. So there is less than a minute. If this meeting ends, kindly join back so that we can solve one problem quickly on this topic. N minus 1 cross 1. So is this clear? So if this meeting ends, we will join back and we'll solve one problem quickly on
Sir,
this.
shall I take any node as a reference node?
Yes, you can. You are free to choose, but in the given problem, they will give, because depending upon which 3 nodes you consider, the equation will vary. Someone was asking a doubt. Is that clear, or still you have any queries?
Sir, suppose if the graph
Okay.
is a square means, then shall I take any node as a reference node, or I
Yes,
have
yes.
to consider all the nodes?
No, no. Okay, let me just quickly solve one problem. So they're asking A. If you see here, they're asking what is the reduced incidence matrix, and they have mentioned node 1, 2, 3. So they are giving, you have to apply KCL at node 1, 2, 3. It is a square. Now we don't know which one to be considered as reference, but they are saying that you have to apply at node 1, 2, 3, which means 4 is their reference. So we are applying at 1, 2, 3. Is this clear?
Okay, sir.
So let us quickly solve. Like if you see, the problem solving will not take much time. Once we solve this problem, you will see that this week it is very easy. So I request everyone to please go through the concept clearly, because this week you can easily score 100% marks, because there is no math. You just have to write the equation properly, and it is just 1 minus 1 or 0. Just these you have to enter. But you have to be very careful while entering. Please don't make any mistake. So this will be our problem 1 for today. Okay, so let us apply KCL at node A. So, sorry, KCL at node 1. So let me do one thing. Let me redraw it so that I can make some changes. If you see here, nodes are also 1, 2, 3, elements are also 1, 2, 3, which I don't like. So what I'll do is I'll write in a different way. Just let me redraw the graph. So here 1, 2, 3, 4. Okay. So these are the nodes. So nodes I'm writing in circle 2, 3, 4, and then 1. And the elements I'm writing pink color and normal numbers. 1, 3, 2, 4. And then this is 6. Okay. So let us copy this and paste it here. So we have to apply KCL at node 1, node 2, node 3. So can anyone tell me what will be the equation at KCL? What will be the equation of KCL at node 1? But I have forgotten to add one more thing, which is IE5.
I3 minus I5 minus I6 is 0.
So current leaving is positive, current entering is negative, right? Isn't it?
Yes, sir. Then I5 plus I6 minus I3 is 0.
IE5 plus IE6 minus IE3 equal to 0. Agree, everyone? Because someone has mentioned in the chat, yes, sir. Okay. Now quickly tell me what is the KCL at node 2 and KCL at node 3.
I1 plus I3 minus I2 is 0.
KCL at node 2, you are saying IE1 plus IE3 minus IE2 equal to 0. Yeah, very good. IE1 plus IE3 minus IE2 equal to 0. And node 3,
Minus I1 minus I4 minus I5 is equal to 0.
okay, very good. So everyone agree?
Yes, sir.
So everyone agrees. So now we have to write in terms of matrix. So what I'll be do is I'll consider this one because it's the same thing. Now what I'll do is I'll ask you what will be the numbers so that you can look at this and then you can tell me what will be the number. So I'll just erase this. So you'll tell me from like this, from first row and then second row and then third row. So you tell me what will be the first element. Node A, whether I1 is there or not.
I1 is 0. Sir.
0.
I2 is also 0.
IE3.
Minus 1,
Okay. Then IE4.
0.
Okay. IE5.
I5 1, 1.
Okay. Everyone agree? Others?
Yes, sir.
And maybe someone else can tell node B. So what will be the values? Like the row. IE1. Parvatam.
1 minus 1,
1 minus 1.
1,
Okay.
0, 0, 0.
Yeah, very good. And then we'll ask Nandini. Can you tell what will be the KCL for node C? What will be the coefficient of IE1, IE2, IE3, IE4, IE5, IE6? And she mentioned in the chat -1, 0, 0, -1, -1, 0. Okay, so -1, 0, 0, -1, -1, 0. Yeah, very good. So everyone agree with this?
Yes, sir.
Okay. Sorry, my writing pad got disconnected. Can all of you see my screen or is it not visible? Can you see my screen, everyone?
Yes, sir.
Okay. So everyone understood, right? How to get this matrix?
Yes, sir.
Yes. So like if you see, this is just the problem. Like they have given one thing and they're asking whether you are getting the answer or not. Now we have to go and check whether we are getting the same answer or not. So if you see, the first one is 0, 0, minus 1, 0, 1, 1, 0, 0, minus 1, 0, 1, 1. And the next line is 1 minus 1, 1, triple 0. 1 minus 1, 1, triple 0. And then the third equation is minus 1, 0, 0, minus 1, minus 1, 0. Minus 1, 0, 0, minus 1, minus 1, 0. So you have to enter the answer in this way. So everyone should be very careful while entering this answer because it is binary. I'm not sure they'll give binary marks or not, but all the questions are simple once you know the concept. So A matrix, I hope everyone will be able to do in the assignment, and no one should make any mistake because if you forget the convention, then it will be a very big mistake, because it will be exactly opposite. So this is the convention everyone should follow. Current leaving the node is positive, current entering the node is negative. Then you apply KCL at the nodes that they have specified, and then write the equation properly without making any mistake. So I hope now everyone knows how to write the KCL at all the nodes and obtain the matrix A.
Yes, sir.
Okay. So now that we have done nodal analysis, now we'll go to the loop mesh analysis. So we do here graph theory and loop method. We have done graph theory and nodal method. So we'll do graph theory and loop method. Okay. So here we have to understand first what is something called fundamental loop. So what is a fundamental loop? So let us go back to the original tree. So in this tree, if I add any link, say I'm adding link 4, and then if a loop is formed, then this is called fundamental loop. Say if I add 4, here there will be one loop formed, right? Similarly, if I add only 5, then this will be formed. And if I add 6, then a bigger loop is formed. So if you add any link to the existing tree, and if the loop is formed, then that is called fundamental loop. Let me take this example there. And how many such fundamental loops are exist? Equal to number of links. Because if we add one link, one fundamental loop is formed. So first let me state it and then write it so that it will be clear. Fundamental loop. Okay. So what is fundamental loop? If a link that like by adding one link to a tree, if a loop is formed, then it is called a fundamental loop.
Sir,
Okay.
the links are nothing but elements of a code tree, right, sir?
Elements of a code tree, yeah, exactly.
But here we by adding one link means
Okay, okay, I'm coming. So, so if you see by adding, okay, I think I have to copy both so that we'll follow the same. Okay, let me just want this. So I think I have changed this. So we are taking this example means like even if you add any one of the link, a loop will be formed. So let me take it to the left extreme, and then we have, let us have three such things. So now what I'll do is I'll use a different color and I'll add, say I'm adding this. So now one loop is formed, right? Similarly, I add this. One loop is formed, right? Similarly, I add this. Now another loop is formed, right? So by just adding one link, one loop is formed, right? In all these three cases. Agree? Just by adding one link, because there are three links. I'm adding one link in each of these things, and these all the three loops that are formed, they are called fundamental loops. Agree? Or any confusion?
Yes, sir.
Yeah. So now the obvious question that I'll be asking is how many number of fundamental loop exist? How many exist? Equal to number of links, right? Right? Each link corresponds to one fundamental loop. So here we have three. Agree? Yes,
Yes,
sir.
sir.
Okay. So now we'll apply KVL in this, KVL in this, KVL in this. So how people have named this? If by adding element 4, one loop is formed, they name it L4. Loop 4 because of 4. Similarly, this will be L5, this will be L6. Agree? I mean, clear? Just the naming. By adding which element the loop closes, that is given, that name is given to the loop. So by adding 4, loop is formed, so it is called L4. Similarly, L5, L6.
Okay, sir.
Okay. So now here the convention is little bit different. What is the convention? Convention is traverse through the loop. So we have to basically apply KVL. I can go clockwise, I can go anti-clockwise. But how should I go? Traverse through the loop in the opposite direction of the current in the link. Say the link is flowing in one direction, we have to go in the exactly opposite direction. What I mean to say is, in this, we will traverse in this direction. In this, we will go in this direction. In this, we will go in this direction. Agree? Just the opposite direction, because current is flowing in clockwise, we'll go anti-clockwise. Just the opposite. In 4, it is going clockwise direction, so we'll go anti-clockwise. In 5, it is going clockwise, so we'll go anti-clockwise. In the L6 also, it is flowing clockwise, so we'll go anti-clockwise. Is that clear or any confusion or any doubt?
Yes.
Clear. So now someone help me with the KVL equation in loop 4, KVL equation in loop 5, KVL equation in loop 6. So KVL in L5, KVL in L6, KVL in L7 as well. Yeah, so someone please help me. So KVL in L5. So we have now voltages, right? So what are the elements? Element 1 to 4. So VE1, VE2, VE4 are there. Please keep that in mind.
So
Maybe we can
suppose we are
start from home.
suppose we are taking the current in the same direction, then what will happen, sir?
Okay, that I'll tell, because why we have to take the opposite direction, that I'll tell. Once we write the matrix, I'll tell. Because on the RHS side, it is 0, right? It doesn't matter whether I'm going in this direction or in that direction, because I can always multiply by -1 on the LHS side as well as -1 on the RHS side. So that's why it doesn't matter. But once we write the matrix, we'll see why it matters.
Okay, sir.
So KVL in L5, anyone? Sorry, L4, right? My bad. L4, L5, L6. KVL in L4. So what is the convention in the KVL? If you are going from higher potential to lower potential, then we'll get minus. If you are going from lower potential to higher potential, then we'll get plus. So that is the logic. So KVL in L4, what will be the equation? Anyone? Shamita, Parvatam, anyone? I hope I'm audible.
Sir, IE4.
IE4, VE4 basically because it is voltage.
Right, VE4, sir.
Okay, VE4.
Minus VE1
Okay, very good.
plus VE2.
Plus or minus?
Sir, 4 and 2 are travels towards the same direction.
So we are traversing in the same direction. So we are going to a lower potential, right, from a higher potential. So is it a plus or minus?
Yes, minus, sir.
Minus. Yeah, very good. Others agree?
Why we are taking in minus, sir?
So if we are going from higher potential to lower potential, then there is a reduction in the potential. So we'll have minus. If we are going from lower potential to higher potential, then we are gaining potential. So it will be plus. So when we are going from B to A, we are going to a higher potential. So plus. When we are going from A to O, we are going to a lower potential. So minus. Similarly, when we are going from O to B, we are going to a lower potential. So that's why minus.
Then how from A to B, sir? It's
We are not
under
going from
both
A
are
to B, right?
the
We are going from B to A because I have defined the direction how I am traversing through the loop.
yes, from B to A, both are at higher potential as a B and U.
Now compared to B, whether A is at a higher potential or a lower potential.
Donuts.
How current is flowing? A to B or B to A?
The voice is breaking.
How is the current flowing? A to B or B to A?
B to A.
Current in the element 4.
You took it from B to A.
No, the direction of the current. 4, element 4 current.
From A to B.
A to B, right? So current flows from higher potential to lower potential or lower potential to higher potential?
Higher potential, lower
Lower
potential.
potential, right? So now VA is at a higher potential to B or a lower potential compared to B?
A is at higher
A is
potential.
at higher potential, yes. But how we are traversing through the loop? We are going in the anti-clockwise direction, right? So we are going O to B, B to A, and then A to O. So we are basically going from B to A. So we are going from lower potential to higher potential. So that's why it is plus VE4. Is it clear?
Yes.
Hello?
Sir,
Hello?
there are actually, sir,
Yes.
one small confusion, sir. Actually, there is a
Mhm.
current direction is mentioned in every link, sir. And
Current
we
direction
also,
mentioned in the?
every link, sir.
Yes, yes.
And we have also used one current direction inside of the loop.
Yes.
And every link
No,
has the positive.
this is not the direction of the current. This is how we are applying KVL. For applying KVL, I can go in clockwise or anti-clockwise direction, right? So this is not a current. This is how we are traversing for applying KVL.
Okay, sir. Suppose if we are taking the loop direction for the fourth link, link one, sir, link one, the direction, loop direction as well as the link direction both are same.
Yes.
But suppose if the polarity is positive, negative, that is 0 is negative and A is positive means whether we have to consider the polarity or we have to consider the current direction. Which one, sir?
Because both are relative, right? So if current is direct going from A to O, A is at a positive terminal, right? Because if we go back to our very first equation from where we have drawn, like why we have removed the voltage polarities, because now I know that if this is the direction of current, this is the polarity, right? A is at plus, O is at minus. So A is at a higher potential. Similarly, A to B, A is at a higher potential, B is at a lower potential. Similarly, O to B, O is at a higher potential, B is at a lower potential, because the polarity is dependent upon the direction of the current. That's why we have removed the voltage polarity, because it is like implicable from the direction of the current. So that's why we have removed.
Suppose the loop direction, that is KVL loop have a
Okay.
direction, right, sir?
Uh-huh.
If it is minus plus means then
No, no. Okay. Okay. So let us now go in the other direction. Okay. So now let us go in this direction. So now what will be the equation?
B4
Plus or minus? You always have to check if
minus
yes, minus VE4,
yes,
and then
and minus uh,
so
plus VE2
if you are going
plus
in the
VE2
direction
plus
of current, it is minus. If you are going in the opposite direction of current, it is plus. Okay, plus VE2, and then
plus VE2 plus VE2, sir, and
okay,
this one is plus VE4.
VE1, right?
Sorry, VE1, sir.
Okay. So now I ask you one question. Are these two same or different?
Yes, sir, both are same.
Both are same, right? So it doesn't matter how you go, clockwise or anti-clockwise, but it matters in terms of matrix, because uh, in this case the coefficients are minus one, 0. Here the coefficients are 1, and minus 1, right? So like there will be one minus sign in the in terms of coefficient when we write the matrix, but in terms of the equation both are same. But in terms of matrix it varies, right? You are getting my point, right? So if you write this in terms of matrix and this in terms of matrix, where you are getting 1, you will get minus 1. Where you are getting minus 1, there you will get 1, because it is just the opposite, right? So which we don't want. So that's why we have to fix a convention and we have to stick to that convention, because if there is no convention, I can get two possibilities of equations, right? Whether should I proceed with this or whether should I proceed with this. So that's why we are sticking, like fixing one convention and following that. You got you got it? Like why convention has to be made?
So no need to consider the current direction. Only we have to consider the polarity, right, sir?
Yes, yes. Or like yeah, both are basically dependent, but like if you are comfortable with the voltage polarity, yeah, then you can consider that. But we are basically traversing in the opposite direction of the current in the link always. Is it clear or still some confusion is there?
Clear, sir.
Others? What about others?
Yes, sir.
So now, can any one of you tell me what is the KVL equation in L5?
V5
Okay, V5.
plus V3
Okay.
minus V2 is equal to 0.
Minus or plus V? Anyone? Is it minus V2 or plus V2? Plus. Nandini is saying plus. What about others? So we are going from B to O or O to B? Samita,
Sir,
how are we going? B to O or O to B? How we are traversing through the loop?
B2
B to O. So we are going to higher potential or a lower potential?
lower potential.
B is at a higher potential. O is at a higher potential or lower potential?
Lower potential.
Okay, how are you saying O is at lower potential?
We are taking it as reference node. Means.
See, O can be reference, but B can also be negative, right? I'm not saying like, see, B can be positive, can be negative. Say O is 0 and current is going from O to B. So current goes from higher potential to lower potential, right? So O is at higher potential or lower potential?
Higher potential.
Higher potential. So we are when we are going from B to O, are we going to a higher potential or a lower potential?
B2O is going at lower potential.
Why? Because O is at a higher potential. Why it is lower potential?
From B2O, it's lower potentials.
Why?
From B2O, it's higher potentials. From O to B, it's lower potential.
Yes. So we are going from B to O and it is going to a higher potential. So it should be plus VE2, right?
Yes.
Like you people are still confused about the polarity because we are already in week 8 and like this has to be the like see if you see this is the most fundamental thing that is like there in each and every week. It is just a plus and minus sign and that will change the entire answer. Like you should be very thorough with this. When we are going from higher potential to lower potential, it will be minus. When we are going from lower potential to higher potential, it is plus. And current goes from higher potential to lower potential. So from that you should know which is at higher potential, which is at a lower potential. So it should be plus or minus. Because if you make mistake here, then like things would be difficult. You will not get the right answer. But this is like very fundamental thing that we have been doing since week 1. So you should be a little bit confident. If you are little less confident, still okay. You go through that and make yourself comfortable. So now equation KVL in loop 6. So we are going A to O, O to B, B to C, C to A.
VE1 minus VE1
Okay, minus VE1.
minus VE2
Very good.
minus VE3
Yes, very good.
plus VE6 is equal to 0.
Yes, very good. So Nandini also mentioned the same in the chat. So she's also right. Okay. So now let us write the same in terms of a matrix. Okay. So let me copy paste the same. elements. Instead of currents, we have voltages. So it just saves time. Okay. So instead of IE1, IE2, I have VE1, VE2, VE3, VE4, VE5, VE6. This is KVL in loop. Right? So let me just fill. So it is KVL in loop L4, KVL in loop L5, KVL in loop L6. So we have voltages V1, V2, V3, V4, V5, V6. So now tell me what will be the expression, constants or the elements of the matrix in row 1.
0, -1, no, -1, -1,
Yeah.
0,
Hmm.
1, 0, 0.
Yes, very good. Others in loop L5, what will be the expression? Maybe Parvatam Vijay.
0, 1,
0,
1,
0, 1, 1,
0, 1, 0.
0, 1, 0. And then loop L6, maybe Nandini. -1, -1, -1, 0, 0, 1. Very good. -1, -1, -1, 0, 0, 1. So now if you see, the loops are for element 4, 5, 6, right? L4, L5, L6. So if you see this matrix, you will notice one very important thing. This is a unity matrix, right? Agree? Sorry,
Yes,
not
sir.
unity, identity matrix. So, like you have asked, sir, like if we go in the clockwise direction or if we go in the anti-clockwise direction, both will result in the same expression. So, why is this convention needed? Needed because, say, if I am going in the exactly opposite direction, here I will get -1, here I will get 1, here I will get 1. So, I will not get the identity matrix, right? Because I might get -1, -1, 1, or -1, 1, -1. So, I should get identity matrix here. So, in order to get identity matrix, I have to get VE4 positive, VE5 positive, VE6 positive. When will I get VE4 positive? When I am going in the opposite direction of the current 4, right? So then only I am getting plus VE4. Similarly, when I am going in the opposite direction of current 5, I'll get VE5. Similarly, when I am going in the opposite direction of IE6, I'll get VE6. So that's why we are going in the opposite direction so that I'll get the positive terminals VE4, VE5, VE6, and I'll get the identity matrix here. That is it clear, or any doubts or any still confusion? Because we have to get identity matrix, accordingly the convention was made. Clear or still confusion?
Clear, sir.
Clear. So now this B matrix is called as fundamental tie set matrix. Fundamental tie set matrix, and these are called element voltages. So basically, if we write the equation that we are basically getting B matrix into element voltages equal to 0. So now what will be the size of B? Because if you see, the number of rows in the B is nothing but number of fundamental loops. And number of fundamental loops are equal to number of links. So number of rows are nothing but number of links, and number of columns are E. Similarly, VE, it has how many rows? Equivalent to number of elements and one column. So now if you ask how many, what will be the size of 0 matrix? It will be L cross 1. This part is clear or any confusion?
No, sir.
Okay. Let me just quickly summarize before we solve one problem on this topic. So we are doing now graph theory and loop method where we'll apply KVL. Previously we have applied KCL. Now we are applying KVL. So in the KVL, first we have to identify fundamental loops. Fundamental loops are nothing but the loops that are found just by adding one link, which I have mentioned here. So the number of fundamental loops will be equal to number of links. So there are three links, so we'll get three fundamental loops. The convention is we have to traverse the route in the opposite direction of the current in the link. So now when we do that, we'll get KVL here, KVL here, KVL here. We get three equations for the three fundamental loops. Now if we write in the matrix form, then we'll get an identity matrix. So in order to get this identity matrix, this convention is made. So we have to get identity matrix. If you are not getting identity matrix, then it's a sign that you have made a mistake. And then we got the B matrix, which is called fundamental tie set matrix, and these are the element voltages. So the meeting will end within few seconds. Once this meeting ends, we'll quickly solve one problem on this B matrix. If you have any doubts, you can ask. Please join back so that we can continue our discussion. Any doubts until this point?
No, sir.
Okay, so please let this meeting end so we can join back and solve one problem. It is B matrix. Yes, yeah. So we'll be solving this problem. So let us quickly solve this problem. So this will be our problem 2 for today. Okay. So first I'll ask you a few questions.
Sir,
Please
some
answer.
hint boxes are there, sir.
Sorry.
So what is the hint boxes are there? What is the
These
purpose, sir?
boxes where you have to enter the values. -1, 1, 0, 0, -1, 1, 1.
No, couldn't get, sir.
Like these matrices that you are getting, these values you have to put in this box. So loop 6 has 6, 7, right? So 1, 2, 3, 4, 5, 6, 7. These are for loop 6. These are for loop 7. You have to put -1, 0 or 1.
Okay, okay, sir.
Got it?
Yes, sir.
Okay. So now how many elements are there in this problem?
7, sir.
7. And how many nodes?
6.
6. So how many twigs will be there? Twigs are the elements of tree. They have already given tree.
5.
5. Very good. And how many links will be there?
2.
2. Because there are 2 links. And E is 7. If you see the B matrix size will be 2 cross 7, right? So which is what they are asking. So we have to apply only 2 loops, meaning 2 KVL we have to do, and then we have to get the expression. So let me draw the simplified directed graph. So you should be also able to do. I hope there is no confusion in that. So this one and this one. Are you able to see my screen?
Yes, sir.
Okay. So this is 2. This is 4. Okay. So let me write the nodes in circle so that we can differentiate between the element as well as the node. So this is 5. This
Here
is
the
1.
polarity is not given, sir.
Polarity is not given, but you know the direction of the current, right? So now you know the polarity. Because when you are going in the opposite direction of current, then you are going to a higher potential. When you are going in the direction of current, you are going to a lower potential, right? Does that make
Sir,
sense? Or
repeat, sir.
when when you are going in the direction of the current, you are going to a lower potential. When you are going in the direction of opposite direction of the current, then you are going to a higher potential, right?
Okay, sir.
Clear or doubt? Like if you have doubt, please ask.
Uh, Clear, sir. Clear.
Clear. Okay. So now we have two loops because of two links. One is L6. So I'm calling this L6 and I'm calling this L7. So in the case of L6, how am I traversing? So this outer loop is the loop. So I will be traversing like this, right? In the opposite direction of L6. Similarly for L7, this is the loop. So I will be traversing in this direction, in the inner loop. Does it make sense or any query? Because for loop
Clear, sir.
6, outer loop is the loop for loop 6 and loop 7, inner loop is the loop. Everyone, is that clear?
Yes, sir.
Okay, now some of you please help me with the KVL. So KVL in loop L6, what is the expression? And then KVL in loop L7, what is the expression? We have to tell the right expression this time. Maybe we can start from node 1 and then go to node 1, 6, 4, 2, 3, 5.
VE1
Okay,
plus VE2
okay, very good,
plus VE6.
very good.
You didn't give direction
Yeah,
for
my bad, my
3.
bad. Yeah. So this is 3, 3. Yeah, sorry. Now tell me.
Plus VE3
Okay, very good.
plus VE5
Okay, very good.
minus VE4 is equal to 0.
Yeah, very good. So now maybe who is there? Parvatam or Nandini? Can you tell what will be the KVL in loop 6? Sorry, loop 7, because we have already done 6. Anyone?
Sir, VE4
So okay, we are going in this direction. VE4
and minus VE1.
minus VE1. But how are we going? We are going in the anti-clockwise direction, right? After 4, 5 should come, right?
Uh, okay, sir.
So VE4 plus or minus VE5?
Minus, sir. Minus VE5
Minus VE5, very good.
and plus VE7
Very good.
minus VE1.
Equal to 0. Yeah, very good. So now let me take the matrix. Here we have 7 elements, so I'll modify that. So elements we have 7 and loops we have 2 only. So I'll arrange this. I'll also arrange this. And this will also change. So we have elements how many? 1, 1, 2, 3, 4, 5, 6, 7. So we have a matrix here multiplied by V1, V2, V3, V4, V5, V6, V7. This is equal to 0, 0. Yeah. Now tell me what are the values.
1 1,
Hmm.
1,
Hmm.
minus 1, 1, 1, 0.
Yeah, very good. So now maybe Nandini, can you tell me what will be the KVL in loop? Okay, again the names will change. So this is L6 and L7. Nandini, are you there? Yeah, she has mentioned in the chat. So she says minus 1, 0, 0, 1, minus 1, 0, 1. So minus 1, 0, 0, 1, minus 1, 0, 1. So this is what she said, right? 1, minus 1, 0, 1. Yeah. So everyone agree? If you see again here, identity matrix is there, right? Because L6 and L7, 6 and 7 corresponds to like the identity matrix as said here, because it is 3, here it is only 2. So we should get identity matrix. If we have not gotten it, it's a sign that you have made a mistake. So you have to cross check again. So let us check the answer. 111, minus 1, 111, 0. So 111, minus 1, 111, 0. Then the other one, minus 1, 00, 1, minus 1, 0, 1. Minus 1, 00, 1, minus 1, 0, 1. So answers are matching and you have to write this. So here you have to enter the values properly. So don't make any mistake. This week is very simple and I'm hoping on you that you will do better this week and everyone should get 100%. Okay. These are very simple problems and all of you are, I think, now confident. So now everyone should be able to do A matrix as well as B matrix computation, right?
Sir, actually, that hint for the answer, you have to put these matrix, right,
Yes,
sir?
yes. So
But,
this in this box you have to enter. Like
but
in this
also,
box, sorry.
oh, for the loop 6 and loop 7, we have to enter the.
Yes, so the first box will have 1, 1, 1, minus 1, 1, 1, 0. Here you will have
So,
minus 1,
above
0,
also, there
0.
are two.
No, no, this is the question. This is the question. This is the answer.
Oh, right, right, right.
So this
Okay,
is the
okay.
question. These two are question. This is the answer. So that's why if you see this color is different, this color is different. Similarly, here if you see this is the question, this is the answer. Because how will I know which loop is on the top? Loop 7 can be top, loop 6 can be bottom, right? So that's why they have mentioned loop 6 is on the top, loop 7 is on the bottom. And these are branch 1, 2, and 7. So now you know, first you have to apply at KCL in loop 6, then KVL in loop 6, followed by KVL in loop 7. Is that clear?
I sir.
Okay. I think there is a lot of noise coming. Let me just quickly close my door. Yeah. So now let us quickly go to another important topic, which is the cut set. Cut set method. So
So
this is,
this
yeah,
is tie set matrix, sir.
this is fundamental tie set matrix. Now we are going to fundamental cut set matrix.
Then that nodal analysis, what method, what
That is
matrix, sir?
reduced incidence matrix. So I have given the names. So A matrix is reduced incidence matrix. So in the exam, they'll ask like that, reduced incidence matrix is A, and then B matrix is fundamental tie set matrix. So this is fundamental tie set. Now we are going to fundamental cut set matrix. Sir, I have a personal question with you, sir. After this session, kindly spare 2 minutes. Yeah, definitely, Parvatam. I'll be there. Graph theory and cut set method. So cut set method. So what is a cut set? Cut set is nothing but any line that breaks the network into two parts. Like I will draw a line, any line that cuts the graph into two parts. What I mean to say, let me quickly take that example, the one we have taken at the beginning. Yeah. This example only we are taking. So I'll directly draw any line that cuts the one line I'm drawing. So it is cutting the network into two parts, right? Similarly, I can draw like this, or I can draw like this. So any line that cuts the graph into two parts, that is called cut set. Now there is something called fundamental cut set. Fundamental cut set. So if the cut set cuts only one twig, then it is called fundamental cut set. So if the cut set,
Sir, we should cut the tree or circuits.
any like a circuit, but so like the given circuit has to be cut. Okay, but now if you see it is
We can
cutting
cut
one.
that side,
Sorry,
that side diagram, right side diagram also we can cut nas.
we can cut, but I have put both so that you can know what is the twig. So if you see this line that it is cutting the network, it is also cutting 1, 2 as well as 3, right? It is cutting all these three twigs, right? If the cut set cuts only one twig, let me first write this one twig, then it is called fundamental cut set. It is called fundamental cut set. Okay. So now if you see, let me quickly complete this. Again, my writing pad will be connection. Let me quickly connect it.
Twig will be come under only tree now, sir.
Sorry, which one?
So you should cut the tree or
Wait, let me quickly complete this. To 5. And then this is 6. Okay. So now this is the original circuit. So if it is cutting only one twig, so in the left side, the line that I have drawn, this is called cut set because it is just a line which is dividing into two parts. Now I have to draw a line which will cut only one twig. So here the twigs are 1, 2, and 3, right? So now I will cut like this. This is 1, this is 2, this is 3. So this is cut set 1, cut set 2, cut set 3. If you see, cut set 1 is only cutting one twig, which is twig 1. Cut set 2 is cutting one twig, which is twig 2. Cut set 3 is cutting only one twig, which is twig 3. So now the obvious thing is number of fundamental cut sets. Number of fundamental cut sets is equal to nothing but number of twigs, which are nothing but n minus 1. Here it is 3. So is the nomenclature clear for everyone? What is cut set? What is fundamental cut set? Or is it not clear?
Sir, please repeat, sir.
Okay, so cut set is nothing but any line that cuts the graph into two parts, here or anywhere. But what is fundamental cut set? The cut set has to cut only one twig. If you see this cut set is going through 1, 2, as well as 3, all the twigs. So this is not fundamental cut set. If you see this cut set, it is going through only twig 1. This is going to only twig 2. This is going through only twig 3. So these are called fundamental cut sets. So because number of twigs is nothing but n minus 1, the number of fundamental cut sets that exists also will be n minus 1, which is 3, because it is cutting only one twig, right? Does that make sense, or is not clear here?
So cut set 1 and cut set 3 are the fundamental cut set. Cut set
And
2
cut set
is
2 also,
the,
because it is only cutting one twig, right? It is not cutting 1 or 3, it is only cutting twig 2.
oh, so no need to consider co-tree, right, sir?
Sorry.
So there are tree and no. Actually, there are one, two. Sorry, sir. Cut set 2, which cuts the fourth link, second link, and fifth link, right, sir?
No. 4 and 5 are linked. 2 is twig.
Only two. Oh, that's why I'm asking, sir. So
Uh-huh.
no need to consider the co-tree
No need
links.
to consider co-tree. Like we are only considering twig, like tree. Twig is the element of tree, right?
Okay, sir. Understood, sir.
Others, is it clear?
Yes, sir.
Yes, sir. Okay. Now, if you see in the case of here also we'll apply KCL, but we'll apply KCL not at the node, at the cut set. We'll apply the KCL at cut set for the cut set. So the convention still remains the same. Positive if current is leaving cut set, current leaving cut set. Implies positive, current leaving cut set is negative. So again, one question can come. Say I'm considering one example. This is my cut set, and the element is something like this, right? Say this is my current IE1, and this is my same current IE1. So the question is, if I consider this region, current is leaving the cut set. If I consider this region, current is entering the cut set. So the question is, which region should I consider? Again, the same. Like how we are getting a identity matrix here, same way we'll get the identity matrix here also. So you have to consider that region where the direction of the twig is positive, because we should get a
You
identity
wrote
matrix.
at both leavings.
Sorry.
You wrote at both
Oh,
leaving.
sorry. My bad. Current leaving is positive, current entering is negative. Thanks for correcting. So you have to consider that region in which the twig current will have a positive sign. So is that clear, or still any doubts or query? Okay, maybe once we write the equation, it will be clear for you. So we are applying KCL at cut set 1, KCL at cut set 2, KCL at cut set 3. So cut set 1, IE1 is leaving, this is also leaving, this is also leaving, right? So what will be the expression, anyone? KCL expression? Hello?
Sir, IE6
IE6,
plus IE4 plus IE1
IE6 plus IE4 plus IE1. Very good. Nandini also says the
equal
same.
to 0.
Yes, equal to 0. Now let us go to cut set 2. Cut set 2, this is still leaving, this is also leaving, this is also leaving, and this is entering. So what will be the expression? Anyone? Cut set 2. So this is leaving, this is leaving, this is leaving, this is entering. So what will be the expression?
IE6,
6, 4, 2, and 5.
yeah, yes, sir. IE6,
IE6.
IE4 plus IE4
Okay.
plus IE2
Okay.
minus IE5 equal to 0.
Yeah, very good. So now let us go to cut set 3. So this is leaving, this is also leaving, and this is entering. So what will be the expression?
So once again, how the T equations comes.
So if you see cut set 1, we have to check whether current is leaving the cut set or current is entering the cut set. So you consider cut set 1. IE6 is leaving this, so plus IE6. IE4 is also leaving this cut set plus IE4. Then IE1 is also leaving, so plus IE1. Now you consider cut set 2. IE6 is leaving this cut set. IE4 is also leaving this cut set. IE2 is also leaving this cut set. IE5 is entering this cut set. So maybe I'll consider the region that we have considered. So this side is the region that we have considered for cut set 1. And this side is the region that we have considered for cut set 2. And similarly, this side is the region that we are considering for cut set 3. So in that
So
region,
we
we are
can
checking.
consider the right side of the cut set. You should consider the right side of the cut set.
No, not the right side. You should consider that region of the cut set where the twig currents will have positive, uh, like you have to consider that side of the cut set where twig current is leaving the cut set. So maybe I will mention you have to leave that side of the cut set.
But IE5 is leaving us as
So
negative.
no. Twigs are 1, 2, and 3, right? We have to make sure IE1 and IE2 and IE3 are positive. So you have to consider that side of the cut set where twig current is leaving. Okay, because we need to have the positive. So if you see this side of the cut set, twig current is leaving. This side of the cut set, twig current is leaving. Twigs are 1, 2, and 3. So this side of the current, this side of the cut set, twig current 3 is leaving. So we have to consider those 3 regions only. So Nandini says IE6 plus IE3 minus IE5. Yeah, very good. So is this clear, Shamita? Or any confusion?
Sir, cut set matrix 2, IE5 is entering us.
So it is minus IE5, no? But the twig current is positive, right? Twig current is what? IE3 is the twig, right? What are the twigs? 1 and 2 and 3. So I have to make sure IE1, IE2, IE3 coefficients are positive.
Yes, sir.
So that's what I have ensured, and that region only I have considered.
So
Is
for
that
the
clear or any confusion?
cut set 3 region, the IE5 current is leaving, right, sir?
IE5 is entering, na? So the yellow region, that side it is entering, right? Now, like if you see, like say this is the element, okay, this is the direction of current, and say this is a cut set. Now, if I consider this side region, current is entering the cut set. If you consider this side of the region, current is leaving the cut set. So in one case you will get positive, in one case you will get negative. But you have to consider that region where the twig current is having positive side. So that is the logic we have, or the convention that we are considering. Does it make sense now? Because this side of the cut set, current is entering the, like this, right? So current is going in this direction. Here current is going in this direction. Here current is going in this direction. So IE6 and IE3 are leaving. IE5 is entering. Not clear or clear? I know this is a little bit tricky, but if you have query again, I'll explain.
Because while you're applying the same concept for the cut set 1,
Yes. So if you see cut set one,
Sir, we got confusion because which area we have to choose, whether the in the C node C you have considered the right side area. For the
yes,
node A you have considered the cut set after the area.
yes. So I have told you have to consider that side of the cut set where the twig current is leaving. So if you consider this region, that twig current is entering the cut set, right? So this region will not consider. Similarly, if you consider this region of our cut set 2, the twig current is entering the cut set. So you will not consider this area. Because how you are getting identity matrix here, same way you have to get the identity matrix for the cut set, which means IE1, IE2, IE3 should have +1. So you will consider that region of the cut set where you will get positive sign for IE1, IE2, IE3. Get it? Because if you consider the other region, you will get minus IE6, minus IE4, minus IE1 equal to 0. Then you will have -1 for IE1 coefficient.
Okay, sir.
Clear now or still confused?
Clear, sir.
Clear. Everyone?
Yes, sir.
Okay. Maybe once we write the matrix, then it will be more clear for you. Okay, so this is the matrix. So instead of node, we are having cut set. So instead of node, we are applying at cut set, CS1. So cut set 1, cut set 2, cut set 3. So can someone quickly tell what will be the value?
100
100.
101
Okay. And the other one?
01
Hmm.
01 minus 1
Hmm. 1, right? And for cut set 3? Hello, for cut set 3?
0, 0.
0
Then?
0 minus 1 1.
Yes. So again, if you see, I have to get identity matrix here. So that's why I have to choose that region so that I'll get identity matrix here. If you consider the other region, what you will get? You will get -1, -1, -1. So there is that minus sign which is coming. So I have to consider in such a way that IE1, IE2, IE3, these currents are positive. So again, if you try to name, so this is called Q matrix. And this is IE, which you already know. So this is called fundamental cut set matrix. Fundamental cut set matrix. And then we have Q into IE equal to 0. And then what is the size of Q? We will have what is the size of Q, what is the size of IE, and what is the size of 0. So the number of rows of Q depends upon number of cut sets, which is in turn dependent on the number of what twigs. So it is number of twigs cross number of elements. This is number of elements cross 1. This is number of twigs cross 1. So clear or any queries?
Number of twigs into elements, no, sir. T.
T, right? T is n-1, so it is T cross E, number of elements.
Yes, sir.
And this is elements cross 1, this is twigs cross 1. Clear?
Yes, sir.
Okay, let me just quickly summarize. So now we have learned about the cut set method, where we have learned about cut set, which is any line that cuts the graph into two parts. But there is something called fundamental cut set, which will cut only one twig. So number of fundamental cut sets will be number of twigs. So here we have 3 twigs. So there are 3 cut sets. Now we have to apply KCL at the cut set, and current leaving the cut set is positive, current entering the cut set is negative. Now the convention is you have to consider that region of the cut set where the current, that weak current is leaving, so that the coefficient of weak current will be +1. In that way, we have considered three regions at three cut sets, and then we have applied KCL, and then we got the matrix, and then you will get an identity matrix here, similar to how you get an identity matrix in the B matrix. So now if you don't have any queries, let us quickly solve one problem. We can solve this problem. No queries, right? We can solve a problem, right?
Yes, sir.
Okay. Others, what about others? Nandini and Parvatam?
Understood, sir.
Okay. Okay. Yes, sir. Everyone has understood. Let us call this the question 3 or problem 3. So how many elements are there?
5,
Nodes.
4,
So number of clicks,
3,
links.
2.
Okay, very good. So let us draw the directed graph in the way we want. Okay. So these are the nodes, and we'll put inside circle so that they can differentiate from the elements. And let us draw the elements. This is 4, this is 3, this is 2, this is 1, and this is 5. So now we have to first thing what we have to do is draw the fundamental cut sets. What cut sets we have. So because there are 3 tweaks, we'll get 3. So what are the cut set? This is called cut set 1, CS1, and this is called CS2, and this we can call CS3. Clear, everyone?
Yes, sir.
Now we have to consider that region where the tweak current is leaving the current source. So I will mark the region. You just let me know whether it is clear. So the top region we are considering. Similarly here, this side of the region. Similarly here, this side of the region. So is it clear? So in that region, if you check, the current is, I'm marking the current. The current is leaving the cut set. Here also current is leaving the cut set. Here also current is leaving the cut set. So that we'll get positive expression, like 1 we'll get if you consider that region. Is it clear or any confusion?
Yes, sir.
Clear. So now can someone tell me what is KCL at cut set 1, KCL at cut set 2, KCL at cut set 3?
IE1 plus IE5 is equal to 0.
IE1 plus IE5 equal to 0. Very good. And then cut set 2?
IE2 minus IE5 is equal to 0.
IE4 is also there.
I plus IE4 is equal to 0.
Yeah, very good. And then cut set 3, maybe we'll give chance to Parvatam or Nandini, any one of you or both of you. IE3 plus IE4 equal to 0. Nandini says IE3, IE4. So Parvatam, do you agree?
Yes, sir.
Yeah. So now let us quickly draw the matrix. So instead of 6 elements, we have 5, but we have 3 cut sets. So let us draw. So we have 5 elements. So I'll arrange this. So the meeting time is less than 1. So probably this meeting will end, but we'll come back if you have queries before we wind this session. So now tell me what will be the values. What will be the values? The meeting might end, but please
1
join back.
0 0 0 1.
10001. Very good. And the other one?
1 0 1 minus 1.
The last one?
1 0 1 1 0.
No, 0 0, right? 0 0 1 1 0, right? IE3 and IE4, right? Clear, everyone? We should get an identity matrix. So if you make a mistake, then you will not get. So that is a sign. Okay, so is this clear, everyone? How we are getting this matrix? Cut set matrix.
Yes.
So let us check the answer. So we got 1 all 0 1. Sorry, 1 all 0 1. And then we got 0 1 0 1 minus 1. 0 1 0 1 minus 1. And then we have 0 0 1 1 0. 0 0 1 1 0. So this is like this summarizes everything that we have discussed in today's class. So I may not summarize, but I'll just quickly glance. So we have learned what why do we need graph theory? Then we have also discussed about graph, how to draw graph, how to draw directed graph, how to draw simplified graph, which we have used in today's class. Then we have discussed about the nomenclature, like what is tree, what is code tree, what are elements, what are nodes, what are twigs, and what are links. And then we moved on to graph theory and nodal method, where we are applying KCL at each and every node to get the A matrix, which is also called as the reduced incidence matrix. Then we have discussed about one problem where we have calculated the A matrix. And in the next, we have discussed about the loop method, graph theory and loop method, where we'll apply KVL in the fundamental loops. And fundamental loops are those loops which you'll get by adding one link to the existing tree. So number of fundamental loops is equal to number of links. And then we have applied KVL to get the matrix B, which is also called as fundamental tie set matrix. And you will get an identity matrix for the elements which are the links. So here 4, 5, 6 are the links. So here you are getting an identity matrix. Say if 1, 3, and 6 are links, then you will get 1 0 0 0 1 0 0 0 1. So because here they are next to each other, you are getting able to see. Okay. Then we solved one problem on that where we have only two loops. So we got a identity matrix here 0 1 1 0 and 0 1. Then we moved on to something called cut set method, graph theory and cut set method. And then we have learned that cut set is any line that cuts the graph into two parts. And then we have also learned that fundamental cut set means it cuts only one tweak. So the number of cut sets is equal to number of tweaks. Okay. And then if you follow the convention, then if you write the expression, you will get the fundamental cut set matrix, or also called the Q matrix, where you will get identity matrix for the tweaks, because 1, 2, 3 are tweaks, you are able to see the identity matrix. But say if 1, 4, and 6 are the tweaks, then you will get 1 0 0, 0 1 0, and 0 0 1. Say if you are not getting this identity matrix, then you have made a mistake. So you have to check whether your convention is proper or not. So kindly solve all these problems again by yourself to check whether you have fully understood the convention and you are getting the identity matrix. And identity matrix will come only for B and Q. Note, it will not come for A. Only for B and Q it will come, not for A. Okay, and then we have solved one problem on the cut set matrix. So any queries? This week session is this week problems are very simple, only 1 0 and -1, but you have to be very thorough with the polarities, conventions, and make sure you make all the equations, everything, write the equations right. Then you will get 100%. This week you can easily score 100% because the problems are very simple. Only you have to understand all the conventions and make sure all the polarities are right. If you are sure, then you can score 100%. So please solve problems. You will be able to solve. I am pretty sure that you are confident and you can score 100%. Any queries?
No.
Okay. Narsaya, Parvatam, Nandini. I think Parvatam had one query. But other than that, any other
Understood, sir.
queries? Okay. No, sir. Okay. Okay, then with that, we can end this session. I wish you all the best for your assignment date, and I am expecting that all of you score 100% in this assignment. So please be confident with the convention. Try to understand why we are using that convention, and then be careful with the polarities. Solve few problems, then you will be able to solve. So with that, we can end this session. Yeah, thank you, Nandini,
Thank
and
you.
I wish you all the best. Yeah, yeah, Shamita, you may leave.
Thank you, sir.
Yeah, yeah, thank you. With that, we can end this session here. Good night, everyone.